Hello, everyone, and welcome to PAMA's Understanding Fasteners webinar. Today's webinar is brought to you by the Professional Awning Manufacturers Association Division. I'm Mike Gaddy with Herculite Products, current PAMA chairman, accompanied by Andy Moon with Baraboo Tenton Awning, chairman of the webinar committee. We are here to welcome you all, and especially to welcome and introduce our speakers today. You will have an opportunity to submit questions to today's presenters by typing them into the questions box of the control panel. You may send in your questions at any time during the presentation. We will collect these and they will be addressed during the Q&A session at the end of the presentation. I would now like to introduce today's presenters, Bob Lund and Ben Sinola. Bob is the current Director of Engineering at Fasteners. He received his Bachelor of Science degree from the University of Wisconsin-Stout and his Master's from the University of Wisconsin-Milwaukee. Bob has been with Fasteners for 18 years and is a member of the American Society of Mechanical Engineers, SAE Fastener Committees. Ben is a current application engineer, graduated from the University of Minnesota at Duluth. Ben has been with Fasteners for 5 years, and he has an emphasis in concrete anchors. He is also experienced in anchor designs, testing, and the process of gaining International Code Council approval for anchors. Please welcome Bob and Ben.
Well, thank you everyone for joining us. I am Bob Lund, and Ben will be talking a little bit later and also helping me out if I stumble or have an Alzheimer's moment, and that's entirely possible. It looks like we have a lot of people on the line, so I'm pleased and impressed and hope that it's worth your time. The topic today is fasteners, and I guess I'll start off by saying that fasteners are important, but not very well understood. Part of that is even at the engineering level, Fastenal now has, I don't know the exact number, but somewhere between 75 and 100 different engineers in various fields. And not a single one of them ever had a class on fasteners while they were in college. So it's something that people have to kind of pick up on their own. And over the last 18 years, I've picked up a fair amount of it, but I amaze myself every day at how little I really know about them. So hopefully that isn't a bad sign for this presentation. But there's a lot of stuff to pay attention to that can cause significant problems. And part of the reasons fasteners are overlooked is because they're generally pretty inexpensive. If you're dealing with parts that cost pennies or even quarters, you don't spend as much time thinking about them as you do thinking about the parts of your product that are a lot more expensive. And it's a shame if something happens where a 25-cent fastener causes thousands of dollars worth of product otherwise to fail. So they are more important than people would expect up front, but oftentimes it takes a failure to realize that you should pay attention to the little stuff as well. So what we will be talking about over the course of the next half an hour to 45 minutes is 2 or 3 really different types of fasteners. We're going to talk about the fasteners that you would use to fasten metal to metal or wood to metal, your typical bolt and screw type products. We'll also follow that up by talking about anchors. And anchors are really the type of fasteners that you're going to be using to fasten into hollow block or brick or whatever type of wall you may be up against. And they are a fair bit different in the way that they are handled. We're also going to talk about rust and how to keep that from happening. And we'll talk about actually two different types of rust, your standard rust and then dissimilar metal rust. So that will be somewhat interesting. And then we're going to talk a little bit about why some fasteners and some fastener companies have options that are ICC approved and others don't, and what that is and what it means. So that's kind of the overview of what it is that we're going to be discussing in the next few minutes. As we move to the next screen, we're going to start with your typical nuts, bolts, and screws. And I guess the best place to start would be to throw a description out there of both. Bolts and screws are a bit different, more than just the name. Generally speaking, bolts are going to be larger, from a 1/4 inch in diameter on up to 4 inches, although you probably don't have any awnings that are going to be using a 4-inch diameter bolt. The screw world is generally smaller, and in the inch world we talk about them as numbers quite often, and they're generally a 1/4 inch on down. So you'll have number 10s and 12s and 8s and other different sizes. So screws are little and bolts are big. On top of that, most of the time a bolt uses a nut on the backside. You can have tapped holes that bolts go into, but the majority of the time a bolt is going to use a nut. And the majority of the time a screw will not have a nut. There are indeed machine screws that have little machine screw nuts, but most of the screws that we'll be talking about today form their own threads. For example, if you are remodeling the basement and you're using drywall screws to hang up sheetrock, you don't first drill a hole and then use a tap to put threads into the 2x4 and then insert a fastener. You just use a screw that plows its way in and makes its own threads. Some cases you don't even need to drill a hole, but in most cases you'll have a pilot hole of some kind that is created, and the screw will form its own threads into that pilot hole. And it turns out the pilot hole itself is very, very important. Again, we'll talk more about that as we get through. But probably the most important difference between the bolt and the screw is that bolts are installed generally by running the nut down until it's finger tight against whatever you're clamping, and then there's a certain torque value that is used to tighten the bolt further. And whether you're actually using a torque wrench and a torque value, or you're just continuing to tighten until you think it's tight, which in some cases works, and in some cases you should really pay more attention to the installation torque. But in either of those cases, what's happening is the bolt is stretching. The material in between the nut and the bolt will be compressing a little bit, but most of what's happening is the bolt is stretching. And when you stretch that bolt, it's not that different than stretching a rubber band. You're putting a load into the bolt that is then keeping that load pressed back against whatever it's clamping. So much like taking a rubber band and putting it around a couple of fingers, when it's fairly loose, you don't feel it, but as you tighten by doubling over that rubber band, you see more and more pressure put upon your fingers. And that's the concept of a bolt. You tighten it to a certain preload or clamping force. And in the screw world, as I'm sitting in the room that I'm in, I'm looking around looking for screws. I happen to be looking at the light switch on the wall. There's a little screw, actually a couple of them, that hold that plastic plate around the switch. When you install that screw in there, you tighten it until it's flush, and you're done. You don't continue to tighten and stretch the screw, because that would break that little piece of plastic, or it'll strip out the sheet metal that it's going into in other applications. So the screws are generally tightened until they're flush, and then you stop. You don't continue to tighten. Okay, let's move on to the next slide and talk about materials. In the bolt world, you have a lot of different grades. You may be familiar with Well, probably the most common numbering system is for SAE bolts. There's a standard J429 that talks about how strong bolts are. And they have a grade 2, a grade 5, and a grade 8. They're the most common of their grades. And the 2 is not heat treated, it's just plain old steel. And it has a tensile strength that probably won't tell you a whole lot of 60,000 pounds per square inch. When you go to the 5, they add a little more carbon into the steel. It doesn't matter to you, but it allows it to be heat treated. Those bolts have a minimum tensile strength of 120,000 psi. So you essentially about double the strength of the fastener. And then to the grade 8, which is 150,000 pounds per square inch minimum tensile strength. So you're gaining another 20-25% worth of strength by going from the 5 to the 8. But there are different strengths, and each strength will be tightened differently because the stronger bolts can take a heavier load. You'll tighten them further and put an increased clamping force on whatever it is that you're bolting together, whatever that bolted joint comprises. In the screw world, you really don't have that. In the screw world, you have either plain old soft screws and machine screws probably aren't used much in your world, so I'm not going to spend much time talking about them. But the thread cutting, the thread rolling, the sheet metal type screws are all case hardened. And what happens is you take a low carbon screw and you put them in an oven with a lot of carbon in the environment, and that carbon seeps into the screw. And when that happens, and you go through the heat treatment process, the carbon that's seeped into the screw, maybe a few thousandths of an inch, it gets harder. And it allows you to have a wear surface and a surface that is able to cut through or drill into other materials. So you can think of those screws really like M&Ms. They've got a softer center and a hard shell around the outside. And that shell is both for wear resistance and to allow you to form the threads and other materials. The strength of a screw isn't really talked about in tensile strength like grade 5s and grade 8s are, and there's only that one case-hardened type of screw. So if we would pull them in a tensile tester, they'd probably be similar in strength to a grade 5, although they work a little bit differently. You do also, in both the bolt world and the screw world, have the option to use stainless steel to prevent corrosion. But there's one thing a little different with stainless fasteners, the corrosion resistant type, is that you can't heat treat them either to give them a shell or to through harden them like a grade 5 or a grade 8 bolt. So they're much softer. They don't corrode nearly as fast, but they aren't nearly as strong. So you can think of them as low carbon level strength parts. There is a special type of stainless steel. They call it a 400 series stainless steel that is heat treatable. But when you go to that type of stainless steel, it corrodes much, much faster than the regular stainless steel. So you have to use platings and coatings and paint to cover that, just like you do the regular steel parts. So I'm going to lump those 400 series that are heat treated into the same world as a regular steel nut, bolt, or screw. The one thing that you have to be aware of there is that just because it says stainless steel doesn't necessarily mean that it's the true, really corrosion resistant. If you see 18.8 or 316 in a description, then you have that type of stainless steel that you might expect from kitchen equipment and other areas where you need high corrosion resistance. Okay, let's move on. This just shows pictures of several types of screws. To confuse you, I put the first one in there that looks an awful lot like a bolt. The true terminology for most bolts is actually a hex cap screw, but the screws that you're going to see more often, the machine screw would be the second option in. I would guess that you may use lag screws a fair amount, and the lag screw is there really to go into wood. It normally needs a pilot hole, although there is a product in the market called a SPAX SPAX screw that does very, very well without pilot holes, and also going into harder materials. If you happen to go into oak or something like that, it does a wonderful job of, it's more expensive, but it does a much better job than a regular lag screw at handling things without holes. So even though the screw is a little more expensive, you might be able to save some labor time by not having to drill pilot holes. A set screw, a wood screw, and then the last one is a sheet metal screw. And those sheet metal screws are the ones that I'm guessing get used a lot. And there's certainly lots of different head styles. You can have hex heads and Phillips drives and slotted drives. The slotted is really the one that's the hardest to use, but there's Torx and square and other types of bits that you might use to install that. You see different types of screws that are used when they go into softer materials like plastic, but again, I'm guessing that isn't something that a lot of you deal a lot with. But just in case there are some that use that, a regular screw thread, if you would look at the angle of the threads, you'd see a 60-degree angle. And the screws that are designed to go into plastics use a little sharper angle, 45 or 48 degrees, so it doesn't bully its way into the material as much. It's sharper, so it cuts a little better into the plastic. Okay, let's move on. I have in this picture 3 different types of holes that are shown. And the hole is tougher to see because it already has the screw installed. But if you look at the left-hand side that says machine screw, at the bottom of the hole, you see a couple of extra screws, threads. And what that's showing there is they first drilled a hole. And then after the hole was drilled, we went back and we tapped that hole so that it had female threads in it to accept the male threads of the screw itself. It's another step in the process. So there's a drill step, a tap step, and then an installation step. The second one in the middle just has a hole drilled, a pilot hole. And then that case-hardened screw thread cuts. You see a little feature on the end that acts kind of, it forms the threads, that little V at the bottom. And there's lots of different types of features on the end of screws that will actually cut those threads. One of the issues with these thread cutting type screws is that they form debris or chips. In this case, I showed those as falling to the bottom of the hole, so it doesn't really matter. If there's a through hole scenario, those chips will just go out the other side. And in some cases, that's not a big deal. But in other cases, you may not want chips of metal laying around. So the third option would be shown on the far right, where we roll the threads, and it's really a semi-triangular shape to those threads, and they go in and they just kind of push the threads into the material. It moves material in and out into the threads of the bowl. You may have heard those called tap tights or other brand names, and they don't have that excess thread cutting type debris. But the thread cutters and the thread rollers, as well as regular sheet metal screws, are commonly used when you're attaching to framework. The regular sheet metal screw should be used for thin material, and the thicker material, if you have plate basically, or a real thick sheet, you can use the thread cutter or the thread roller. But a little common sense needs to be used here, that if you've got a piece of sheet metal that's real thin, and you look at the screw threads, if you're only going to get half a thread of cut, tapped thread into your sheet metal, it's not the right type of screw to be using. You want to have at least maybe half a diameter's worth, or at least a couple of threads of engagement if you're going to worry about creating threads in your mating piece. Otherwise, a standard sheet metal screw is probably your better bet. Let's move on. And here you see the different types of cutting tips, basically, on a lot of these. The regular sheet metal screws will generally have a type A or an AB without a thread feature. You see the B doesn't have the pointy point, it has a blunt point. And then we get into the majority of the next ones, the D, F, G, the BT or BF or 23 on the other side. They all have some feature on the end of it, and those are used to actually form the threads. And then at the upper right, I mentioned that tap tight that rolls threads, and that drawing kind of shows how that screw thread form is actually a little. It's a cross between, well, if you had a round screw and a triangle screw that got married and had babies, that's what it would look like. That tap tight. Then at the bottom, we've got a self-drilling screw that has a drill point on the bottom of it, and that's probably a real common type of screw that's used in your world. And you have options, whether it's a hex head or other type of head or drive style, but the hex head is by far and away the most common. And that drill point is automatically sized so that it drills the right pilot hole for the screw threads to engage. And you have fewer issues with grabbing the wrong drill bit to create a pilot hole. So that's a real good advantage. We do see some issues with self-drilling screws. And I guess the easiest way to explain that is they have different tip lengths, and that screw needs to be done drilling before it starts threading or tapping the hole. So you need to hold up your pieces together and look at the drill tip. If you have a tip that's too short, that drill bit feature of it, if it doesn't get all the way through drilling before it starts to form threads, it will strip out. So if all of a sudden you're seeing a lot of stripping issues, that's almost always what the issue is. You need a longer point. Okay, let's move on to corrosion. I don't need to explain the regular type of rust. If you leave a shovel in the backyard and it rains and you forget about it and you come back a couple weeks later to start or continue on your project, you're going to have a rusty shovel. That's something we all understand. There's a different type of corrosion called dissimilar metals or galvanic corrosion. And that's what I'm showing here. If you have, without getting too far into the details, if you have different types of metals, they have different free electrons. And those electrons want to move from one spot to another if there's a difference in free electron numbers. I'm trying to make this real oversimplified. So you get an anode and a cathode, and you're going to get electrons that want to move from an anode to a cathode. And on the next screen, I actually show a little table, I believe. Go ahead and skip to the next one. Next slide, please. There you go. You're not going to be able to read the table on the right very well, but up at the top of that list of materials, you'll see aluminum and cadmium and zinc and lighter materials like that. At the bottom, you'll see stainless steel, and in the middle, you'll see some regular steel and brasses and bronzes. What happens is the materials on the top of this will be the anode, and anything below it would be a cathode. And the further away on the chart these materials are, the more the discrepancy in their free electrons will be. And you will start to see those free electrons move from the top of this chart to the bottom of this chart. And how that will show itself to you is over in the picture on the far left. I have a stainless steel screw that we installed into aluminum. And both aluminum and stainless steel do very well in the environment by themselves. But when you put the two of them together, you see those free electrons moving from the aluminum base material into the stainless screw, leaving oxidation on the aluminum. And in the middle, I tried to do a little hand drawing to show what would happen if you had aluminum and brass up against each other, and you connected them with a stainless steel bolt, a nut in this case. And you have those two materials, actually all three materials that are very corrosion resistant when used by themselves, but you have the two plates, the aluminum and the brass, and aluminum is up at the top of this chart, brass in about the middle. So if you expose them to weather, exterior conditions, you're going to see electrons moving from the aluminum to the brass, and the aluminum will start to corrode. If we look at the bottom where the nut and the brass plate come together, you've got a stainless steel nut up against a brass plate. In that case, the brass is the anode. It's higher on that chart than the stainless, so the electrons will flow from the brass to the stainless steel, leaving the brass corroding. Up at the top, where we've got the head of the bolt and the aluminum, those are even further away on the chart, the aluminum being up near the top. It is the anode, and the stainless steel on the bottom, the cathode. And since there's a greater discrepancy in their free electrons, you'll see more corroding on the aluminum than you had down on the bottom where the brass was. So I guess my point is you need to pay attention because I would imagine you're using quite a few materials that are by themselves corrosion resistant. But when you are putting stainless and aluminum together, sometimes you need to pay attention and be careful and perhaps isolate the two, or still look at using some type of plating, coating, a spacer in between there so that you don't get corrosion. Okay, let's move to the next slide. What do you do to protect parts and keep them from corroding? The most common thing is to electroplate them, and that's done to regular carbon steel parts more than anything. You'll put a clear or a yellow plating on there for the old timers in the crowd that remember back to where I can remember. They used to use cadmium, and cadmium was pretty good plating. It lasted a long time. However, they found out that the cadmium caused health issues, and the government told us, I don't know, 30 years ago, that we should stop using cadmium plating because of health issues. It is still available. It's not illegal to use it, and we still sell a fair amount of cadmium plated parts. I guess it's not surprising that our largest user of cadmium plated parts is the same government that tells us not to use it, but that's a separate discussion. So we went to clear and yellow zinc, and yellow zinc has recently, in the last 10 years or so, maybe a little more, been found to also cause health issues. So slowly that is going away. If you have ever seen the movie Erin Brockovich, that's what that was about. There's something called hexavalent chromium in the yellow coating that makes it better from a plating standpoint than the clear, but it is has health issues, not so much for the users. You're fine if you've used a lot of yellow zinc plated parts, but in the plating process itself, with wastewater and issues like that, you started seeing a lot of cancer and things like that. So the yellow zinc is starting to go away. There are other coatings, and some of them have brand names that will sound fancy. We call ours EcoGuard, but there are lots of different brand names out there. If you hear it called a coating, it's probably one of these, and maybe somebody just put a private label name on it, like we did with our EcoGuard. But these are thicker coatings. They're basically a paint that they put zinc and aluminum flakes into the paint. And they will last oftentimes 5 or 10 times as long as the platings do. So they're very good at keeping things from corroding, but they also can't be used up against stainless steel because of that galvanic stuff that we talked about in the previous section. They don't do really well, and since they cost more, I wouldn't bother using them against stainless steel because they're not going to give you any better corrosion resistance than a regular plated part. There it would be best to try and go with a stainless material, or you can get aluminum fasteners to go into aluminum. There are a few different options there. And we've already mentioned that you do have stainless steel options for your fasteners, and they by themselves should last a whole long time if we pay attention to the galvanic reactions that may happen because of them. Let's go to the next slide. So now we're into getting generally into the anchor world. And I'll talk about this just a little bit, and then I'll let Ben correct all my mistakes. But the ICC codes that you may see, if you're looking at Hilti anchors, for example, Hilti anchors are more expensive. Hilti's a good company. They're a competitor of Fastenals, but we're not here to be a commercial for Fastenal. But if whether you're using Fastenal or other suppliers, you have the option of our or our competitors' fasteners. It may be an ITW fastener. It may be Powers anchor, and then Hilti is kind of its own thing. Hilti has spent an awful lot of money going through the ICC approval, and that's part of their business plan. Is they develop an anchor and then they have to have it tested. And the ICC is really a lab process where they verify that the anchor is able to do what they say it's going to do. And there's a whole lot of testing involved. To get a series of anchors approved or to get the stamp, it's kind of like an underwriter's laboratory concept. But the ICC will put their stamp on it just to validate that those numbers are what the Hilti folks say they are. It costs about $1 million to get a group of parts ICC approved because of all the testing that needs to be done. So it's Hilti's business plan, and ITW has done a lot of this as well, to actually spend the money. And they pay for it initially, but you end up paying for it in the long run. But you do get a comfort feeling that yes, this is going to last. It's going to hold what it's supposed to hold. So that's why if you look at the Fastenal website, we've got anchors that are the same style, the same size, and the same material that cost quite a bit less, but they don't have the ICC stamp on them, so to speak. And that's the rationale. With some of our anchors, we are going through the ICC approval process. And with others, we just want to have an option for people that don't have to have the paperwork to prove to an inspector that they are what they are supposed to be. So that's an overview anyway of why an anchor from someone like Hilti is quite a bit more expensive, and it should be. They have to make up that $1 million that they spent, along with whatever margin they have on top of that. Generally speaking, the anchors that are made out of the same material, they're the same type and they're the same size, are probably going to do very close to the same type of job for you. But since we haven't gone through on our generic line, so to speak, we haven't gone through the testing, we can't claim that they're going to be the same strength. So that's a decision that you'll have to make. Let's move on to the next slide. And as we move into the anchor world, since that's Ben's area of expertise, I think I'm going to let him start doing the talking, but there are several different types of methods to anchor into concrete and block and other types of materials. So these are some of the different options. And Ben, I will let you correct any mistakes I made on the ICC end of things and start talking about the various anchors.
All right, thanks, Bob, and thanks everyone for joining us here today. What Bob was speaking about with ICC was pretty much dead on. A couple things I will add is, as with ICC approved screws, they don't want just anyone providing screws to be used in construction, and they also don't want just any laboratory being used. There are all kinds of testing laboratories across the nation, but they will only allow a few of them to actually conduct the ICC testing. And it's actually a pretty extensive audit they will do on the lab to actually approve them to test for ICC. And the thing with ICC is they don't just cover approvals for anchors. They cover a whole gamut of things. For going into concrete, there are two main ICC approvals that you may have heard of. There's ICC approval for uncracked concrete and ICC approval for cracked concrete. Now, the cracked concrete approval is much harder to get because to meet those standards and to pass that testing, anchors are actually installed into cracked concrete and then pulled to the various test that ICC outlines, and is much more demanding on the anchor. So what I'll talk about today is I'll kind of cover the mechanical types of anchors, screw anchors, wedge anchors, drop-ins, sleeves, pin anchors, and leg shields. But there are also other types of anchors that could be covered, including adhesive and direct fastening, or the powder actuated stuff. So let's move on to the next slide. So some of the main things to keep in mind when you're installing anchors, and most reputable companies will have this data, is the minimum embedment depth. And if you look at that picture, which hopefully you can read, that would be H-nom. That is the section of the anchor that is actually embedded in the concrete. It doesn't include the thickness of whatever fixture or whatever thing you're fastening to the concrete. You want to keep an eye on your minimum hole depth. And for most, like for a wedge anchor or a screw anchor, usually the hole depth is anywhere from 1/4 inch to 1/2 inch deeper than the minimum embedment depth. Two really important things to keep an eye on are your anchor spacing and edge spacing. As you go up in diameter and you go deeper into the concrete, your anchor spacing and edge spacing requirements will get larger. You also want to keep an eye on what the company recommends for a minimum member thickness, or your minimum concrete slab thickness. Deeper embedments, larger diameters will require a thicker slab. A lot of the times, in an ideal world, you'll be able to abide by the minimum anchor spacing, the minimum edge distance, and stuff like that. But a lot of the times you can't, and a lot of the companies will publish what kind of strength reduction you will get if you have to violate the rules a little bit. Usually with all concrete anchors, you have to install a pre-drilled hole, and you will want to use, usually the companies will call out a hammer drill bit made to the dimensions and tolerances of, usually some companies will call it an ANSI bit. It's really ANSI B212.15 is the standard. Those are the type of bits that you'll want to use. After you drill the hole, it's really smart to clean it out with compressed air. If you get a lot of dust and debris in there and you try to install some of these anchors, a lot of the times they can get bound up, or your performance will go down. So we'll get into looking at some of these right now. Let's go to the next slide and look at some concrete screws. So these I think are relatively new in the industry. I know they've been around a lot longer than I've been in here, but it's kind of a new thing. You can actually, these screws, you would drill a hole into concrete, blow it out with compressed air, and then you'll actually take a power driver and you can drive these into concrete. And as Bob mentioned earlier in his presentations about case hardened screws, that's what these fasteners are. They have a soft core hardness, but they're very, very hard on the surface, because you need a very hard surface in order to be able to tap threads into concrete. The 3/16 screw usually uses a 5/32 bit, and the 1/4 inch screw usually uses a 3/16 bit. These can go into a variety of substrates: concrete, hollow block, whether it's grouted or ungrouted. They can go into brick and in even wood. So they're very versatile. They pretty good loading on these for their size, and quite versatile. Usually you can see the blue coating on this screw. They usually come with a high corrosion resistance coating. Many companies come up with their own names, but like ITW uses a blue Clima seal. I forget what Powers calls theirs, but they tend to hold up quite well in outdoor applications where there's going to be a lot of moisture and stuff. So we'll go to the next slide, please. So now we'll look at our large diameter concrete screws. Now these are kind of the big brother of the small diameter screws. Usually these are in the diameters of 3/8 to 3/4 inch. These will carry ICC approvals in uncracked and cracked concrete. I should have mentioned for the small diameter, those will usually only carry ICC approval in uncracked concrete. It's hard to get fasteners 1/4 inch and below to pass the cracked concrete specifications, just because when they install that and they widen the crack, they just don't hold. So, but for the large diameter, companies usually, the big players like Hilti, ITW, Powers, will have the ICC approval and the uncracked and cracked. Um, just like the small diameter, these require a pre-drilled hole, and then you can just screw it right in. The nice thing about screw anchors is that they're removable. I wouldn't recommend, removing it and installing it into the same hole and expecting the same holding power, but it's nice for if you're, screwing down a temporary structure or you got to move something. It's nice not to have to get the cutting wheel out and cut something off. You can just easily unscrew it. So these things very versatile. You see them used a lot with like rack and shelving, holding down the base of those. Typically, they don't come in high corrosion resistant coatings or platings, so they're really usually used indoors. But I think a few companies might carry some hot dip galvanized, so you do see them used outside as well. Let's go to the wedge anchors. So wedge anchor, a little bit different than your screw anchors. It's the same in regards that you drill a hole in the concrete, then you would pound this down to the embedment depth that you want, and then to get the holding power, you tighten the nut, and companies will have a certain torque spec that you want to tighten that down to. And what happens is, you can see in the picture, there's a little clip on the bottom of the anchor right above that tapered section. And as you tighten that nut, you're taking that tapered section of the stud and it is slowly going up into that clip and expanding that clip so that it will press out into the hole. And that gives the anchor its holding power. Now, out of all the anchors mentioned today, given the same strength of concrete and same embedment depth, the wedge anchors will give you the most holding power. And in sizes 3/8 and above, these will have ICC approval and uncracked and cracked concrete. They should really only be used in concrete or hollow block grouted. Because they have so much holding power, they really do need a good firm substrate, and they won't do very well in anything else. Obviously, if you tried to install this into hollow block, your clip, you wouldn't have anything to grip onto and it won't work. But you see it used a lot in rack and shelving, safety related attachments, pipe supports, fire sprinklers, stuff like that. Typically they're used indoors, but they are made in stainless steel, so people do use them outside in some applications. So let's move on to the drop-in anchors. These are a little bit different animal. What it is, if you look at the picture, you'll see kind of it's a steel cylinder that has some tabs on the bottom. Well, on the top of the steel cylinder, there's an internally tapped hole, usually UNC threads, so 1/2 inch 13, 3/8 16, 1/4 20, just machine screw threads like that. And what you do is, with all the other anchors, you drill a hole in the concrete. You have to be a little bit more careful, making sure you get the correct depth. You would blow the hole out with compressed air. You would set this in there, and then you would take that setting tool, which is that long steel piece, kind of bluish on the left. You would stick that into the top of the drop-in, and you would pound and hammer. And what you're doing when you're hammering is there's a small plug inside that drop-in anchor that will start to get seated down into that tabbed section, and those tabs will expand in the hole, giving you your holding power. These do not carry any ICC approvals, but you will see them with UL and FM approvals because they get used extensively in the fire sprinkler applications and suspending conduit and stuff like that. So you see them used a lot overhead. If anybody's ever tried that, it is a pretty physically demanding thing when you have to do a bunch of these overhead. So I got a lot of respect for the people that do that. These come in carbon steel and stainless steel, and that's about it for those. Let's go to the next slide, please. Sleeve anchors are pretty much they are a more light-duty version of the wedge anchor. They can be used, I should have mentioned the drop-in anchors, they should only be used in concrete. Sleeve anchors, they can be used in quite a bit more, kind of like concrete screws. You can do concrete, hollow block, grouted hollow block, brick, And just like always, you would drill your hole with the correct size bit, install this in, and then turn the nut, which will then expand that tapered section up into the sleeve, pushing it out into the outer wall and giving it its holding power. These come in a variety of geometries and are pretty versatile things. They come in stainless, carbon steel, so they are pretty useful, but they are lighter duty. They don't carry any ICC approvals. So then we'll just touch on one of the next slide, pin anchors. You all have probably installed one of these a time or two. They can be used in all kinds of substrates, concrete, hollow block, brick masonry, stone. Very easy to install. You drill your hole in your concrete, you stick that in over what you're fastening, and then you just pound down that pin at the top into the sleeve. And what that does is expands the tabs at the bottom to give it its holding power. Very light duty, no ICC approvals, but can be very useful for fixing things too, your concrete, hollow block, stuff like that. For last one I'll cover, and you don't see these used too much, but they can be helpful. They are an expansion type anchor. You would drill your hole, stick this in there, and then these take leg screws that normally get used in the wood. And as you screw in that leg screw, it expands the two halves of this thing, pushes it out into the outer wall, and you get your holding power. They can be installed in a number of substrates, your concrete, hollow block, brick masonry, but they don't carry any approvals, so pretty much used in light duty applications. That's pretty much all I had for the mechanical style of anchors. It was kind of just a general light overview. I hope some of you might have been a review for most of you, but hopefully that was helpful.
Good. Bob and Ben, thank you so much. We have a few questions that came in here during the presentation. Going back to the Bob, you touched on the the SPAX screws. One question was, does anybody use the SPAX legs for retractable awnings? I don't think that you guys would know those questions, but it was more of a survey to the whole group, and I don't think we can get that poll out. But any thoughts on those SPAX anchors?
I guess I would say that they can be used basically wherever you're using regular leg screws. So use them interchangeably, I guess. But I would only pay for the extra from the SPAX if you don't want to bother drilling the holes first. Then it might be a good cost savings for you. They're a relatively new product. I guess it's been half a dozen years since I've first seen them. They've probably been around longer than that, but they're getting more and more common, and you see them going into the Home Depots and the Lowe's and the Menards, and they're used a lot by people around the house, whether it's putting up a wall bracket for your flat screen TV. And I think they're getting used more and more in industrial or construction type applications as well.
And it seems like it would there'd be less stud splitting situations if we started using those too. So that's a great thing to use, I think. Going on to the next question here, thinking about the let's see, what's the difference between 304 active and 304 passive when you're talking about galvanic corrosion?
Very good question. And I think the easy way to talk about that is by saying that basically every fastener that you're going to get is going to be passive. What happens when you make stainless steel fasteners is you're using a tool steel or a regular hardened steel material to pound those fasteners into shape. And over time, tooling wears. And what really happens is little flecks of that tooling get pounded into the stainless steel fasteners. So they need to be cleaned afterwards. And there's lots of different ways to do that. You can mechanically blast them. You can put them in a citric acid, even orange juice will actually clean out the regular steel flecks out of the top of the surfaces of the stainless steel. If you ever get stainless steel that looks to be rusting in spots, that's probably not the stainless steel itself that's rusting. It's the little flecks of tooling, and eventually that rust, if you just take a Scotch-Brite pad or something and scrub it, you'll get that little fleck out of there, and then you've got a clean stainless steel piece that won't show any rust at all. So the passive is really code for cleaned, and in the fastener world, you really won't see anything that's active. I guess theoretically, the base material, if you're going into that could be uncleaned. I'm not sure what happens to the plate steel in the plate steel world, if you'll see that or not. But I think you can essentially ignore the active stainless steel. So someone was looking hard at that table. So thanks for paying attention. Gosh, that means that of the 70-some people that are listening, there's at least one that I didn't put to sleep. So good job.
Good. Next question here. Do you recommend a gasket be placed in between the fastener and the base material to avoid or delay the galvanic corrosion? And if so, what gasket materials would work best?
Another good question. And I'm going to give a hedging my bet answer. There are different types of shims almost, or you could put a washer that's been painted in between. That might help. If you put something real soft in there, like a nylon washer, then that messes up your holding power, because when you torque down a fastener, you're going to be squishing into the softer material of that nylon washer. So you'll help solve the problem on the galvanic side of things, but you may create a problem on the holding strength side of things. So you have to be careful of what type of gasketing material that you might be using. If it's a thin piece of something that would squish down pretty easily, yet form a barrier, I'm not all that concerned. But a hardened piece of a hardened washer, for example, that may have been painted, will do a good job of isolating the two materials. So it's probably going to be a case-by-case basis as to what you might do to isolate it.
Yeah. All right, we got a few more questions here, and we'll try to get to them all before, I think we've got about 6 minutes left. Next question, when you say grouted hollow block, do you mean that the cells are filled or that the blocks are grouted together? Will a wedge anchor blow out a hollow block wall?
Yeah, I mean that the blocks are filled with grout. You wouldn't want to use a wedge anchor in a hollow cell.
Right.
It wouldn't hold very well.
Okay. All right. Is there a rule of thumb for how many pounds different fasteners can hold? For example, I've heard 3/8 inch leg screws hold 100 pounds per linear inch.
All of the types of fasteners that you're using, including, I guess, the anchors, will have some type of value that is published for it. And you can go to Fastenal or your other distributors that you may be using and look for that. We've got something online called a technical reference guide that in regular nuts and bolts world will help with that. But this generally the larger you go in diameter and as you go in the same diameter up in grade, you're obviously increasing the holding power. In the anchor world, you'll see, and I'll let Ben, I don't know if this is out there on our website or not. We've got something called a contractor's guide that will have tables, just like the, ITW has this on their website, as does Hilti and Powers. So the different anchors have a max load. And I would probably play it a little safe and make sure that the load that you're using doesn't line up exactly with what you need, that you use a fastener that's going to give you a safety factor, and go higher.
Yeah, I would say that many times the holding power of an anchor is highly dependent, especially with concrete, on the compressive strength of the concrete. And many times the concrete is the weak link. You only see like steel failure when you really get to the deep embedments, and the anchor has a lot to hold on to, where it'll actually overcome the strength of the steel. Usually you'll see like the concrete breaking out, that being the weak link. So it is highly kind of dependent on the compressive strength of the substrate you're going into.
To follow up just a little bit on that, we get asked about pull-out strengths quite a bit. And if you're going into sheet metal or a 2x4 or whatever it is that you're going into, most of the time the screw is going to be stronger. So if you pull on a screw, it'll pull out of the 2x4 way before you would break the screw. And a pine 2x4 is going to have a lot less holding power than if you're going into oak. So, and if there's a pre-drilled hole, a smaller diameter hole is going to give you more holding power than a larger hole. It'll also take more torque to install into that smaller diameter hole. So, again, like Ben said, most of that pull-out kind of concept is dependent more on the mating material.
Hey, Ben, is there any suggestions for fastening into stucco?
That's a great question, and I honestly haven't really thought about it too much, nor have I ever attempted to do it myself. So I'm going to have to, I'm going to have to take a pass on that one and do a little bit of research.
That's and again, they can contact you guys. I think your information is right on that presentation. Let's see, going on to the next one. What's a good source for the tensile shear strength of fasteners? I think we did mention this before. I've had trouble finding ratings for my fasteners in the past. Did you mention the book?
Yeah, we have a technical reference guide that would be good, but if you go to fastenal.com into the engineering section, which unfortunately is buried deep within the website, you almost have better luck if you just Google Fastenal Engineering. We have all kinds of articles on that, and you should be able to find that pretty easily. Bob probably has more to add to that.
No, that's probably right. From the main menu of fastenal.com, you would go to services, and if you hover over the top of services, you can see Fastenal Engineering shows up. And once you get into the Fastenal Engineering world, there's lots of links that you can choose to get you to strengths and torques.
Okay. Next question, probably the last one here. Is there an ICC approved zinc anchor related for exterior use?
I would say yes, there is. Although, I mean, you can use a zinc-plated wedge anchor outside. The manufacturer might not recommend it, but there's nothing saying that you can't do it. So yes, you would be able to use an ICC zinc-plated anchor outside. It may not be the best decision, but it could be done.
Good. I think we're wrapping up here.
It wouldn't hurt. It wouldn't hurt if you're going to use a zinc plated, because the clear zinc plated doesn't really last a whole long time. After it gets installed, I might put some paint on it.
Yeah, that's a very good option.
Okay. One more question here. How best to know torque spec on concrete screws like Tapcons to prevent stripping of the block or the concrete?
So what ITW and Powers and some of the other people have done is they've come up with an installation tool, and the installation tool is made in such a way that the driver will automatically disengage once the screw is seated. Now, some people don't use those, but if you're really worried about that, I would recommend using that tool. I believe it's for ITW, it's the ITW Con Drive, and for the Powers, it's like the Powers Tapper Plus installation tool or something. But if you don't have access to that, what I would recommend is make sure you set the chuck on your wireless driver to be kind of low, so that you will start spinning out as soon as that screw is seated. The idea is you want to let up as soon as the screw is seated against whatever you're fastening down. If you start rotating it once it's seated, you're going to strip out the hole. The installation tools they sell do work pretty well. That's what I actually would recommend.
All right. Are you guys able to take a couple more calls or a couple more questions?
Absolutely. It's not happy hour yet.
All right. All right. All right. Question here. What will hold in a hollow cell?
Your sleeve anchors will hold. Your small diameter concrete screws will hold. The pin anchor would hold. Those are kind of the main ones. What I would recommend is if you can, is using a small diameter anchor screw like a Tapcon. That's your best bet. Sleeve anchor is also pretty easy. A tip for if you do have to drill into hollow block, it does help if you take your drill off hammer mode. If you drill through the hollow blocks with your drill in hammer mode, you tend to really kind of break out a lot of the substrate on the back side or spall it out. It helps if you just put it into drill mode and drill through. You get a lot cleaner hole. It is a little bit harder on the bit, but I don't know. Kind of what I think, at least.
And just realize that you're never going to get the same kind of holding power in hollow block as you would if you're going into pure concrete.
Yeah. You definitely want to make sure you study up on what the manufacturer publishes for recommended spacing and their allowable loads when you do that kind of stuff. And spacing. It can get a little bit dangerous if you're trying to put a bunch of screws in one cell. It's not a good situation.
Another question on galvanic corrosion. Where does anodized aluminum fit in the galvanic table?
The anodizing doesn't necessarily change the fact that you've got aluminum, but the anodizing does put a surface on the aluminum that is a bit of a barrier. So it's not that different than putting a plating on, and you will get longer life. It's a relative term out of anodized aluminum than you will out of non-anodized aluminum. But you still have that bare aluminum that eventually will come through. And just like putting a plating or a coating on something, if you put a plating or coating on there, it will keep the corrosion away for a certain number of years. Or if you're in Mobile, Alabama, or Los Angeles, where you've got both pollution in the air in Los Angeles, and it's close enough to an ocean that you get a lot of salt in the air, you're going to face issues a lot sooner than if you're in Topeka, Kansas. Again, the same thing will hold true with the anodizing.
All right. I think that does it for our call today. So Bob and Ben, thank you so much for doing this for PAMA, and we're so appreciative of you guys doing this for us. Thank you, audience, for staying on a little longer to answer these questions and listen to this. And this wraps up our fastening webinar. If you have any suggestions for future webinars, feel free to shoot us an email with some suggestions. So thank you again. Thanks, Bob. Thanks, Ben.
Thanks, everyone.
Thank you.